Hi guys, up to now what we have covered in fault analysis is first we saw the per unit representation of the power system, then we saw the concept of symmetrical components, and then we saw how different sequence networks are designed for each and every component in a power system, that is generator, transformer and the transmission line. So in this lecture we will be solving a few problems that have come in GATE examination from these topics. So let us arrive at our first problem. The sequence voltages of an unbalanced three-phase system are given as V1 0.87 pu, V2 minus 0.57, V0 is minus 0.3 pu. We need to find the phase voltages. So here we need to calculate phase voltage from the symmetrical components. So the matrix that we will use will be, we will use our A matrix, that is VB, VC will be 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. Then V0, V1, V2. That means VA will be V0 plus V1 plus V2, which will be minus 0.3 plus 0.87 minus 0.57, which is equal to 0 pu. So VA will be 0. VB will be V0 plus alpha square V1 plus alpha V2. Now this can be written as VB is equal to V0 is minus 0.3, V1 is 0.87, alpha square is 1 angle 240 plus V2 is 1 angle 120 into minus 0.57. So this will come out to be 1.325 angle minus 109.84 degree pu. Now VC will be V0 plus alpha V1 plus alpha square V2. Now as I told you, in the calc, the only thing that you have to do is you have to replace 120 and 240. So minus 0.3 plus 0.87 into 1 angle 120 plus 1 angle 240 into minus 0.57. So this will come out to be 1.325 angle plus 109.84 degree pu. Now these voltages we have arrived at in pu. It is asking the voltages on a voltage base of 11 kilovolt line to line. Now if the base voltage of line to line voltage is 11 kV, the base voltage of per phase will be, it will be 11 by root 3 kV. Now VA was 0 pu, so it will be 0 kV. VB will be 11 by root 3 into 1.325. So how much will this come out to be? 11 by root 3 into 1.325, that is 8.42 at an angle minus 109.84 degree kV. VC will be 11 by root 3 into 1.325, so it will have same magnitude, but angle will be 109.84 degree kV. So you must remember the matrices A and A inverse, because whenever the question comes from the symmetrical component, you can directly use those matrices. No need to remember the individual equations, just remember the matrix. And if you remember one matrix, you can form other matrix just by replacing A by alpha square and alpha square by alpha. In our next problem, it is saying an unbalanced system is having the sequence components like this. What is the power consumed by phase A on a base of 100 MVA? Now, simply I can write power consumed by phase A will be V1 I1 conjugate, V2 I2 conjugate V naught I naught conjugate. Now V1 is 1.2. I1 conjugate will be 3 plus J4, that is 5 angle 53.13. Then V2 is minus 0.4 into 5 angle 53.13. Then V0 is minus 0.1, 5 angle 53.13. So this will be 0.7, that is, how much will this come out to be? 0.7 into 5, that is 3.5 angle 53.13 degree PU. Now base is given to be 100 MVA. So if we multiply it by base, it will be 350 angle 53.13 MVA. In real and imaginary terms, it will be 350 into 0.6, that is 210 megawatt, plus 350 into 0.8 will be 280 MVAR. Okay, so that will be your power consumed by A phase. Okay, just I have used the concept of power in terms of symmetrical components, and I haven't taken 3 because it is just asking the power consumed by A phase. If it were asking the power consumed by all 3 phases, then we will take the factor of 3 and we will take 3 V1 I1 conjugate, V2 I2 conjugate plus V0 I0 conjugate. In our next problem, it is saying a 3-phase transmission line supplies delta connected load Z. The conductor C of the line develops open circuit fault. That is why the current in C is 0. The currents are shown in the diagram. We need to find positive sequence component in A. We know IA1 will be 1 by 3 IA plus alpha IB plus alpha square IC. That is 1 by 3 tan angle 0 1 angle 120 multiplied by tan angle 180 plus 1 angle minus 120 into 0. So it will be 1 by 3 tan angle 0 plus tan angle 1 300. This will come out to be 5.78 angle minus 30 degree ampere. So that will be the positive sequence component of the current in phase A. Okay. So just you have to remember the matrix. This equation even I have written directly from the matrix. How? In matrix, if we write A inverse will be used, that will be 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. So this gives me the positive sequence, that is 1 then alpha square. In our next problem, it is saying, suppose we define a sequence transformation between ABC and P and O variables. ABC is the phase, P and O is positive, negative, 0 sequence. As follows, alpha is e raised to power j pi by 3, k is a constant. Now we are given that Vp, Vn, V0 is some matrix into Ip, In, I0. We need to find the relation between Va, Vb, Vc and Ia, Ib, Ic. Now, we know that Fa, or rather what is the need to write down, it is given here only Fa, Fb, Fc is this matrix. So if you write Fa is k times Fp plus Fn plus F0, Fb is k times alpha square Fp plus alpha Fn plus F0, Fc is k times alpha Fp plus alpha square Fn plus F0. Now if you carefully observe, this is the same transformation that we did to arrive at the phase voltage or the phase quantities from the symmetrical components. Just it is that k is extra here. Now for inverse transformation, what to do is take this k on the left hand side, then write the inverse of this matrix. How? What we will write is F0. F0 will be 1 by 3. K will be taken in the denominator because K will become 1 by K here. FA plus FB plus FC. FP will be 1 by 3K FA plus alpha square plus alpha FB plus alpha square FC, and Fn will be, that is negative sequence, 1 by 3K FA plus alpha square FB plus alpha FC. How I have written this down? From the A inverse matrix, 1 1 1 1 alpha alpha square 1 alpha square alpha. Okay, just a factor of k is additional because of the problem given to us. Now we have to write in the order Vp, Vn, V0, that is P then N then 0 sequence. So what will be the order? We will write it as Fp, Fn, F0 will be 1 by 3K, then 1 alpha alpha square 1 alpha square alpha 1 1 1 FA FB FC. Now we have to arrive at VA VB VC from VP VN V0. Then we can use this transformation. We will replace VP VN V0 by VA VB and VC. So this equation can be written as 1 by 3K 1 alpha alpha square 1 alpha square alpha 1 1 1 VA then VB VC should be equal to, what is the matrix given to us in the problem? 0.500, 0.50, 0.50, 0 0 2. IP, I and I0 can also be replaced like this, that is 1 by 3K 1 alpha alpha square 1 alpha square alpha 1 1 1 into IA, IB, IC. Now to derive VA, VB, VC, we will take inverse of this matrix. Now this matrix is itself inverse of this. This matrix here, suppose this is A, this is A inverse. So inverse of this will give me this matrix. So VA, VB, VC will be it will be 1, what is there, 1 1 1 alpha square alpha 1 1 1 1 alpha square alpha 1 alpha alpha square 1 into K into 0.5 0 0 0.50 0 0 2 into 1 by 3K is also there. Then this matrix. Now K gets cancelled out, 1 by 3 will come outside. So what will be the matrix product that we have to calculate? 1 by 3 1 1 1 alpha square alpha 1 alpha alpha square 1, then 0.5 0 0 0.50 0 0 2. Then the next matrix is 1 alpha alpha square 1 alpha square alpha 1 1 1. Now we multiply the second and third matrix first of all. First row into first column will be 0.5, first row into second column will be 0.5 alpha 0.5 alpha square, then 0.5, then 0.5 alpha square 0.5 alpha, then 2 2 2. Now multiply these two matrices. First row into first column will be 3, then first row into second column will be 2 plus 0.5 alpha plus alpha square, that is minus 0.5, so 1.5. then again it will be 1.5. Then 0.5 alpha square plus 0.5 alpha is minus 0.5 plus 2, that is 1.5. Then 0.5 alpha cube plus 0.5 alpha cube is 1 plus 2, 3. 0.5 alpha 4, that is 0.5 alpha. 0.5 alpha square is 0.5 alpha square plus 2, that is 1.5. Similarly, this row will be 1.5, 1.5, 3. If you divide it by 3, it will be 1.5, 0.5, 0, 0.5, 1.5, 0.5, 0.5, 1. That will be your Z matrix. Now this is a very complicated procedure and it is very long. So let us try to find it by some short method. Now if you observe, first of all, if you transform both these matrices IP, IN, I0 and VP, VN, V0, K will get cancelled out because K will come on both the sides. That means K has no role. Other than that, it is a simple matrix that we used in case of transformer, transmission line and generators. That is the basic matrix of symmetrical components. There is no trick involved. Just that K can be easily removed because it will come on left hand side as well as right hand side. Now if you see, these terms are similar to what we arrived at in transmission line. Positive sequence impedance was Zs minus Zm. Negative was Zs minus Zm. 0 was Zs plus 2Zm. Okay. And it is asking the relation between VA, VB, VC and IA, IB, IC. That was the original matrix, that is Zs, Zm, 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 Zs, Zm, 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 Zs. Okay. So it is asking the relation in the phase voltage and phase current given the relation between sequence components. We were going in the opposite direction. We knew the relation between the phase current and voltages. We were deriving the relation between sequence component. Now just by comparison, I know Zs minus Zm is 0.5, whereas Zs plus 2Zm is 2. Now if we add these two, Zm will become, or let us subtract these two, then 3Zm will become 1.5, Zm is 0.5, and from first equation Zs is 1. So this matrix will be this only, Zs is 1, Zm is 0.5. So this can be arrived directly if you remember the results for the transmission line. In our next problem, it is saying a three-phase transmission line is shown in figure. The voltage drop is given by this equation. This matrix was giving the voltage drop. Shunt capacitance of the line can be neglected. If the line has positive sequence impedance, that is Z1 is 15 ohm, Z0 is 48 ohm. Now we know Z1 is Zs minus Zm, which is 15. Zs plus 2Zm is 48. It is asking Zs and Zm. If we add these equations, subtract these equations, 3Zm will be 33. That is Zm will be 11. And Zs will be from first equation 26, because 26 minus 11 will be 15. So answer will be 26 ohm and 11 ohm. In our next problem, it is saying for the network shown in the figure, the zero sequence reactance in PU are indicated. What is the zero sequence driving point reactance of node 3? So first let us try to draw the zero sequence network. Here first of all generator is there. Its neutral is solidly grounded. So Zn is 0. Let me take a reference bus. Since neutral is grounded, so here we will show Zn is 0. Then generator zero sequence reactance is J.1. Then transformer is star delta grounded. Star means we will operate the shunt switch, keep the series open, then we will place 0.15 J. Then we will operate the series switch because star is grounded. Then transmission line will be J.05. Then again generator is there and its neutral is grounded. So we will have generator reactance like this. Neutral is grounded. So here Zn is 0. This is J.2. Here we have our bus number 3. It is asking the driving point impedance of bus 3. Now these two reactances are in series. So if you see bus number 3, this is series 0.2. This is again 0.2. So for bus 3, they both are connected in parallel. Hence I can say it is J.1. When two equal impedances are connected in parallel, equivalent is half of those. So it will be 0.1 pu. Okay. In our next problem, it is saying a three-phase alternator generating unbalanced voltages is connected to a unbalanced load through a three-phase transmission line. The neutral and star point of the load are grounded. This is the neutral of source. This is star point of load. Both are grounded. So this voltages can be written as minus plus, minus plus, minus plus. Because in star connection, we will connect the negative of all the voltages together. The phase voltage are 10 angle 0, 10 angle minus 90, 10 angle 120. We need to find positive sequence component of load current. To find positive sequence component of load current, we need to find all the phase currents. So let us first try to calculate IA. IA will be 10 angle 0, that is EA, divided by this reactance, that is J2. So it will be 5 angle minus 90. Similarly IB, this is 10 angle minus 90 divided by J3, that is J1 plus J2, 3.33 angle minus 180. The next current is IC, which is EC 10 angle 120 divided by J4, that is J1 plus J3, 2.5 angle 30. Now to determine the positive sequence component IA1, it will be 1 by 3 IA plus alpha IB plus alpha square IC. That is 1 by 3 5 angle minus 90, 1 angle 120, then 3.33 angle minus 180 plus 1 angle 240 into 2.5 angle 30. So how much will this come out to be? It will be 3.51 angle minus 81 degree. Okay. So these sort of questions can come in the GATE examination based on the symmetrical components. And here the effort is very less. You just have to remember the matrices for the transformation. In our last problem of this lecture, it is saying three identical star connected resistors of 1 pu are connected to a unbalanced three-phase supply. The load neutral is isolated. Symmetrical component of line voltage are given. We need to find the components of phase to neutral sequence voltage. Okay. Now first of all, let us talk about positive sequence. In positive sequence, what happens? VAN, VBN, VCN. Now if you determine VAB, it will be VAN minus VBN. This will be VAB. So in positive sequence, VAB leads VAN by 30 degree. And in per unit system, there is no concept of phase or line voltage. Hence, the PU value remains the same. That is why VAN will be in magnitude same as the line voltage, but in angle it will be lagging the line voltage by 30 degree. Similarly, if we talk about negative sequence, it will be VAN, then VCN, then VBN. Now if we wish to calculate VAB, it will be VAN minus BN. It will lag the phase voltage by 30 degree, or we can say the phase voltage leads the line voltage by 30 degree. So VA2 will be having same magnitude, but angle will be leading the line voltage by 30 degree. Okay. So remember this concept, in per unit there is no concept of phase or line. All have the same magnitude in per unit. But phase shift in positive sequences, line voltage leads the phase voltage by 30 degree. In negative sequence, line voltage lags the phase voltage by 30 degree. In zero sequence, there is no component in line voltage, but zero sequence phase voltages can be present. Okay. So these sort of problems can be framed. Out of this, the most important are symmetrical components and the equivalent zero sequence reactance in case of a power system network. Okay. In the next lecture, we will start with the fault analysis, and we will see how to analyze the faulty conditions existing in a power system.